So this is a video talking through the multiple choice component of paper 74053 or paper 3 for A-level chemistry AQA. Chances are if you're watching this video there's just a specific question that you're struggling with, so feel free to use the chapter scroll along the bottom to find the explanation for each one. The reason I've made these videos is just because obviously when you're marking your answers you can see what the mark is, but you don't necessarily know why that's the case. So starting off with question 7, which row shows the number of fundamental particles in one Mg25 plus ion? Hopefully a relatively straightforward one, but in a magnesium 25 ion you have 12 protons, as you always would in magnesium. You would have 30 neutrons, and because it's a 2 plus ion you have 12 electrons to begin with, minus 2, so that means you'd have 10 electrons. So C would be the correct answer there. Question 8. What's the relative molecular mass of benzene 1,4-dicarboxylic acid? So benzene is C6H6. Whenever you put a substituent on, it loses a hydrogen. So you're going to have C6H4 with your two carboxyl groups. So C6H4, two lots of COOHs, given us the molecular formula of C8H8O4. So 8 lots of 12, 96, 8 hydrogens is 8, and then 4 oxygens, 4 times 16 would be 64. So add those values together and you get the MR of 166. Question number 9. Which substance has significant electron delocalization? So hopefully you're aware that graphite has free moving electrons between its layers. Iodine and tetrachloromethane are both molecular, so they wouldn't have electron delocalization at all, and sodium chloride is ionic, so again no electron delocalization. Question 10. Which reaction has a standard enthalpy change equal to the standard enthalpy of formation for barium chloride? So in year 12 you will have learnt the definition for enthalpy of formation. That's where you form 1 mole of a compound from its constituent elements in their standard states. So to form barium chloride, you need barium as a solid and you need Cl2 as a gas. That means our correct answer there would be C. Question 11. Maxwell-Boltzmann distribution for a gaseous reactant. So what's represented by the total area under the curve? This is one of the things you have to learn when you're studying the Maxwell-Boltzmann distribution. It is indeed the total number of particles present. But just going through the other options there, you've got total energy of the particles. That's something you don't have to learn at A level, but that would be the average energy of one particle multiplied by the total number of particles. Activation energy for the reaction is down to the right, so somewhere around there, depending on the reactants you have present, and the total number of reacting particles are just those to the right of the activation energy. So again, D is the correct answer for that one. Question 12. Rate of the reaction is greater when a catalyst is used. So how does a catalyst increase the rate of reaction? It decreases the activation energy, therefore you're going to increase the number of successful collisions per second. So lots of these options here talk about the collision frequency increasing, so that will only really happen if you were to increase the concentration or you were to increase the temperature. The particles aren't going to be colliding more in the presence of a catalyst. So we're not going to be increasing the collision frequency. And again, we're not going to be increasing the average energy of the particles. The particles themselves don't gain more energy, just more of them can react because the barrier or the activation energy has been lowered. So same thing applies with option D as well. So C is the only one that really explains why a catalyst increases the rate of reaction. So when HF is added to water for question 13, the following equilibrium is established. So we're given the concentration of HF, we're given the concentration of F minus, and being asked to find the equilibrium constant, Kc. You might see the equation and realise that it's actually a weak acid. So the equilibrium constant for a weak acid is actually Ka. You don't necessarily need that for this question. If you understand the idea that for every 1 mole of F minus formed, you'd get 1 mole of H plus. Or the concentration of H plus is the concentration of F minus. So using that information, we can simplify the Kc or the Ka expression to be F minus squared products over our reactants HF. Plug the numbers into your calculator, so the values at the top of the screen or the page. 2.3 times 10 to the minus 3 squared divided by 7.7 times 10 to the minus 3. That comes out on your calculator as something like 6.86 times 10 to the minus 4. So rounded would give us answer D. Question 14. Which oxide of the named element is in its highest oxidation state? So oxidation states can be worked out based on the position it is in the periodic table. So for example, group 7, chlorine, it can gain 1 electron, so its lowest oxidation state is -1, or it can lose up to 7 electrons. So its highest oxidation state is +7. You don't necessarily come across an example of chlorine being in its +7 oxidation state, but HClO4 is an example. An example you might be familiar with is when it's in its +5 oxidation state from the group 7 topic in year 12. So it's +5 when it exists as something like HClO3. In the question we've got chlorine paired with 2 oxygen, so its oxidation state would be +4. That's lower than its maximum oxidation state, so that wouldn't be correct. Magnesium's in group 2, so it can lose up to 2 electrons. Its maximum oxidation state would be +2, which it is in this case, so that would be the correct answer. Just going through the other 2 options though, you've got nitrogen, which is in group 5. It can gain up to 3 electrons, so it can go down to -3, or it can lose all 5 of its outer electrons and can go up to +5 as its maximum oxidation state, for example in nitric acid, HNO3. Sulfur in SO2, its oxidation state is +4 in this instance. Sulfur is in group 6, so it can gain 2 electrons or it can lose up to 6 electrons, as you've seen in H2SO4. So nitrogen in N2O4 would have an oxidation state of +4, as it would in sulfur in SO2. Both of those are lower than its maximum oxidation state. So again, B is the correct answer for that one. Question number 15. What happens when water is vaporized? So the equation for that would be H2O liquid turns to H2O gas. So we're not breaking the covalent bonds, we're just breaking the hydrogen bonds between the molecules. So option B is correct. When you break those intermolecular forces, energy is required. So if energy is being put into the system to break the intermolecular forces, that would mean the enthalpy change is positive. Similarly, if we were to look at delta S, something going from a liquid to a gas, you're increasing the disorder. So it becomes more disordered when it becomes gaseous. So C and D are incorrect statements there. Question number 16. Which species can behave as a Bronsted-Lowry acid? So Bronsted-Lowry acid, hopefully you're aware of the definition, is an H+ donor. It donates hydrogen ions. So that automatically rules out C, which doesn't have any protons, and A. Incidentally, A can behave as a Bronsted-Lowry base because it can accept protons to become HSO4-, or H2SO4 if it accepts 2 protons. But again, that's a base, not an acid. So we're torn between option B or option D. HCO3-, can it donate a proton? What would happen if you were to lose a proton? Does it become something you're familiar with? It would become the carbonate ion. So B is correct. Can NH3 donate a proton? No, it can't, because those nitrogen to hydrogen bonds are too strong. So NH3 would not donate a proton, but it can in fact act as a base. It can gain a proton to become the ammonium ion. Question number 17. What change causes the pH of 10 cm3 1 molar NaOH to be halved? So if you were to look at the pH of NaOH there at 298 Kelvin, we can rearrange the Kw expression, Kw over the concentration of OH minus, to give us the hydrogen ion concentration, then you minus log your answer. So 1 times 10 to the minus 14 divided by the concentration, which is 1, that gives you H plus, minus log your answer, the pH is 14. So how do we go from 14 to pH 7? So essentially we need to remove all of the hydroxide ions, we need to make it completely neutral for it to be pH 7 at 298 Kelvin. So essentially we want to allow all of the moles of the hydroxide to react. So looking through the options there, diluting it, that will only reduce the pH a little bit, so that wouldn't work. Again, if you added 10 decimeters cubed of water, quite a lot of water, it's still not going to be neutral. You're still going to have hydroxide ions, it will still have a basic pH greater than 7. Adding 5 centimeters cubed of HCl with the same concentration wouldn't halve it, but you need the same moles of HCl being added there. So D is the correct answer. Question number 18. A 1 mole per decimeter cubed, sorry, a 0.1 mole per decimeter cubed solution of a weak acid has a pH of 2.5. What's the value of Ka for this? So we have the concentration of the acid, Ha. We've got the pH. So if we do 10 to the minus pH, we can find the hydrogen ion concentration. So 10 to the minus 2.5 would give us the concentration of 3.162 times 10 to the minus 3. Going back to the equilibrium Kc question from before, if it's a weak acid, we can assume that H plus equals A minus. So we can simplify the Ka expression if the weak acid is on its own to H plus squared over the concentration of Ha. We just found the concentration of H plus, 3.162 times 10 to the minus 3, so we're going to square that and we're going to divide it by the concentration of Ha given to us in the question. Plug those numbers in and you get 9.998 times 10 to the minus 5. 9.998 times 10 to the minus 5 can be rounded to 1 times 10 to the minus 4. Question number 19. Which statement is not correct about the period 3 elements sodium to chlorine? So make sure you skip off argon in this question. We're not considering argon, just the element sodium to chlorine. So going across the period, sodium has the largest atomic radius, that's correct. So as you go across the period, the atoms will get smaller. So chlorine would be smallest, sodium would be largest. Sodium has the lowest melting point. That's incorrect. Sodium has metallic bonding. So the metallic bonds are going to be stronger than the intermolecular forces between the elements or between the molecules of things like sulfur, phosphorus and chlorine. So I'm just drawing the melting point graph below just to remind you how that looks. you've got your metals over here, sodium to aluminium, silicon's over here, then it drops down to phosphorus, which is molecular, sulfur is molecular, and chlorine is molecular as well. So using that graph I've just drawn below, silicon does have the highest melting point, and does chlorine have the highest first ionisation energy? Ionisation energy increases across a period with the exception of group 3. So aluminium would be lower than expected, and group 6, sulfur would be lower than expected. So in this instance, chlorine would have the highest first ionisation energy because remember we're ignoring argon. It's only sodium to chlorine we're looking at. So B would be the only incorrect statement here. Question 20. Equal volumes of pairs of solutions are mixed. Which pair forms a buffer solution? So for a buffer solution, you need a weak acid in excess with its salt, or a weak base in excess with its salt. So option A, we've got ammonia and ammonium chloride. That's a weak base and it's salt. So that sounds like it should be the correct answer, but let's just go through the other options just to check. You've got ammonia, which is a weak base, and methylamine, which is a weak base. So that wouldn't be a buffer because you've got two bases together. Ethanoic acid and methanoic acid, you've got two weak acids together. And HCl and sodium hydroxide, you've got a strong acid and a strong base. So that would just give you a salt solution. So again, A is the correct answer there. So question 21. Barium metal is added to a large excess of water. Which observation is correct and complete? So group 2 alkaline earth metals added to water, you're going to form an alkaline solution, so barium hydroxide, and hydrogen gas would be given off as well. So hydrogen gas, obviously that's going to give us some effervescence, so B or D is correct. Barium hydroxide, is it going to be a white precipitate? Is it going to be a colourless solution? Well, that's based on your understanding of group 2 hydroxides and their solubilities. So as you go down the group, the hydroxides become more soluble. So barium hydroxide would be a colourless solution. So B is the correct answer there. Question 22. Which species is the strongest reducing agent? So reducing agent is something which itself is oxidized. So the question is saying, okay, which one is most likely to lose electrons? So it wouldn't be F2 or I2 because they are going to be gaining electrons. They're going to be acting as oxidizing agents. F2 is in fact the strongest oxidizing agent. Very likely to gain electrons because it's a small molecule, or a small atom. So it's between F- and I-. Which one is most likely to lose electrons? Be I- because it's got a large ionic radius. And you've seen it's the strongest reducing agent as it reduces concentrated sulfuric acid from the group 7 topic. So you get a range of sulfur products where sulfur can be reduced from +6 all the way down to -2 in H2S. Question 23. Which statement about the shapes of ions is not correct? So cobalt with 4 chlorines or chlorides is square planar. That statement is incorrect. So you only get square planar really if you've got a platinum or a nickel complex with 4 ligands. So that would be tetrahedral. But let's just look through the other options just to make sure. NH4 plus is tetrahedral, that's correct. There are 4 bonding pairs, no lone pairs. CO with 3 lots of the bidentate ligand diaminoethane. So because it's a bidentate ligand, you would have 6 coordinate bonds. Therefore that would be octahedral. And cobalt with 6 waters or hexa aqua cobalt ion is octahedral. There's 6 coordinate bonds, so again that would be octahedral. So A is the only incorrect statement there. Question 24. Which compound can decolorize acidified potassium manganate solution? So which compound can we go from MnO4- and it gets decolorized when it goes to Mn2+, or a very pale pink colour. So in order for manganate to be reduced to Mn2+, it's an oxidizing agent. Silver nitrate would not cause that to happen. Copper sulfate would not cause that to happen. We've seen manganate be reduced in the redox titration part of the course. So 2 common examples, 2 on the specification, would be the Fe2+ ion or the ethane dioate ion. So which compound contains Fe2+ or C2O4? It's going to be FeSO4. It wouldn't be D because that's in an Fe3+ oxidation state. Question 25. Which statement about catalysts used in reactions at equilibrium is correct? So they're not always in the solid state. So you've seen examples of catalysis where you have aqueous catalysts like Fe2+ or Fe3+, or the manganese ion in autocatalysis. They increase the rate of the forward reaction but decrease the rate of the reverse reaction. That's an incorrect statement. They increase the rate of both the forward and reverse reactions equally. They have no effect on the value of equilibrium constant Kc. That is a correct statement. The only thing to affect the value of Kc is temperature. Do they make the forward reaction more exothermic? Catalysts have no effect on the overall enthalpy change. So if you remember enthalpy level diagrams, if you've got an uncatalyzed reaction, let's say that's exothermic, use a catalyst, it provides an alternative route with a lower activation energy, but the overall delta H remains the same, so it wouldn't make it more exothermic. Question 26. Consider this reaction scheme. Which step is shown with a correct reagent and a correct condition? So I'll just go through the reaction scheme. So step 1, we're going from a ketone to a hydroxynitrile. So in order to do that, you need acidified KCN, or HCN is often used, but we'll have a look at the condition in a minute. So it could be the correct answer. Step 2, we're going from the alkyl group to an alkene. So we're removing or dehydrating it or eliminating it. In order to carry out elimination of an alcohol, you need concentrated sulfuric acid with a high-ish temperature of 180 degrees. So it wouldn't be KOH dissolved in warm water. Step 3, you're going from a cyanide group to a COOH. So that would be hydrolysis, but that's not in the question, so we don't need to worry about that one. Step 4, we're going from a carboxylic acid group to an ester group. So we're carrying out esterification. To carry out esterification, you'll need an alcohol, specifically we'll need methanol. And the catalyst for esterification would be sulfuric acid. So not an alkaline catalyst. Finally, we're going from an alkene group to an alkane group. So we're getting rid of the double bond. That will be hydrogenation of an alkene, which does use hydrogen and a nickel catalyst. So that is the correct step there. HCN dissolved in warm water. So why is that one incorrect? So for this to work, the nucleophilic addition reaction of a ketone to a hydroxynitrile, you need a large excess of cyanide and a large excess of H+. So normally that comes in the form of KCN, so you've got loads of cyanide ions, and H2SO4, so you've got loads of H+ ions. If you just had HCN on its own, dissolved in warm water, it's a weak acid, so you'd have a very low concentration of H+ and Cn-. So that wouldn't actually allow much of the reaction to occur. You get a very small proportion of the hydroxynitrile forming. So A was incorrect. Question 27. Which process does not involve a heterogeneous catalyst? So that means it's in a different phase to the reactants. So normally this means when the catalyst is in its solid state, it acts as a heterogeneous catalyst. So if we were to crack alkanes, which are normally liquids at a larger, when they've got a larger MR, to gaseous alkanes, which are smaller or smaller liquid alkanes, the catalyst used is zeolite or aluminosilicate, which is a solid. So that is a heterogeneous catalyst. Contact process, we're using SO2 and half O2 to make SO3, all gaseous, but the catalyst is V2O5 solid. Decomposition of ozone, we're going from O3 to O2, and that's catalyzed by the chlorine radical. So the chlorine radical is gaseous as well, so that would be homogeneous catalyst. So that is the correct statement. And finally, the Haber process, we're going from nitrogen and hydrogen, which are gaseous, to ammonia, which is also gaseous, and the catalyst there is iron solid. So again, C is the only homogeneous catalyst here, all the others are heterogeneous. Question 28, equation for the complete combustion of butane. You've got 1 butane, 6.5 moles of oxygen to make 4 CO2 and water. What's the mole fraction of butane if you've got the minimum amount of oxygen needed for complete combustion? So assuming you've got 0 products to begin with, if we've got 1 mole of butane, you need exactly 6.5 moles of oxygen. So the total moles present for complete combustion, assuming that's the minimum amount of oxygen, would be 7.5. So the mole fraction of butane would be 1 over 1 plus 6.5, or 1 over 7.5. Plug those numbers into your calculator and that comes out as 0.133. Question 29, which is not a possible product of a reaction between KOH and the bromoalkane shown below. So when you've got a hydroxide and a haloalkane, the hydroxide can act as a nucleophile, undergoing nucleophilic substitution if it's dissolved in water, or it can act as a base, and the haloalkane would undergo base elimination if it was dissolved in ethanol and heated. So if it was to act as a nucleophile, the bromine would be replaced by an OH group, so that would form the alcohol as seen in part A. If it was acting as a base, you would remove the bromine and you'd remove a hydrogen on an adjacent carbon. So I'll letter those 1 or number those 1 and 2. So if the hydrogen was removed from position 1, you'd form the alkene as seen in D. If the hydrogen was removed from the label 2, you would form alkene C. So the hydroxide would not cause the formation of a ketone. So B is the correct answer here. Question 30. Many scientists believe the concentration of ozone should not be allowed to decrease. Why do they not want it to decrease? Well, options B and C, ozone is an efficient disinfectant. That's a correct statement. It is used in water treatment, but that's not linked to why the scientists don't want the ozone layer to decrease. Similarly, it can react with chloroalkanes. It catalyzes, or the chloroalkane catalyzes the breakdown of ozone, so they do react together. But again, that's not why they want the ozone layer to stay intact. Ozone is not linked to global warming. They're two separate issues. Global warming is to do with molecules with polar bonds absorbing radiation transmitted from the Earth's surface, and ozone absorbs ultraviolet radiation. That's correct, that's what the ozone does, and as there was a hole in the ozone catalyzed by the reaction of CFCs, there was seen around the globe increased incidence of things like skin cancer. Over time, since the Montreal Protocol in the 1980s, the ozone hole has been slowly recovering and less UV light has been hitting the surface of the Earth. Question 31. Compound X can be converted into an alcohol in a two-stage process. So something plus concentrated sulfuric acid makes an intermediate. You then add excess water to make an alcohol. So you might have done something like a mind map, so you're thinking about the reactions where an alcohol can be made. So an alcohol can be made from things like an alkene. If you added excess water to that alkene, could you make an alcohol? Not necessarily. You would need more extreme conditions, so like that would be hydration, concentrated phosphoric acid, etc. What would happen if you added concentrated sulfuric acid to an organic molecule? Compound X plus concentrated sulfuric acid to make something that could then turn into an alcohol. So thinking about that mind map, that would be an alkyl hydrogen sulfate. So adding water to this thing called an alkyl hydrogen sulfate would make an alcohol. How do you make the alkyl hydrogen sulfate with concentrated sulfuric acid? That will be from an alkene. So that happens via electrophilic addition, where the H2SO4 acts as an electrophile. And again, you might remember drawing this mechanism out once or twice. So the alkene comes along, it attacks the delta positive hydrogen, and you get the OSO3H joined onto the other carbon, which gives you that compound there. So compound X must be an alkene, that's going to be propene. Question 32. What is a correct equation for the oxidation of 1-phenyl ethanol? So if we've got ethanol, obviously 2 carbons, hydroxy group, the phenyl must be on the same carbon as the hydroxy group. So we need the C6H5 on that carbon there. So looking at the oxidation in a second, but that eliminates the possibility of A or B, because the OH is on carbon 1, the phenyl is on carbon 2. So A and B would be 2-phenyl ethanol. If we were to oxidize this structure here, so the OH is on this carbon, you would turn that into a C double bond O, you get rid of the hydrogen, so that would give us C6H5COCH3, and that would be option D. That would be phenyl ethanone being produced. Question 33. The skeletal formula of 2 compounds are shown. Which method would distinguish between samples of these compounds? So you've got 2 aldehydes. They both have 4 carbons in, 1, 2, 3, 4. So they both have the formula C4H8O. So looking through the options, their fingerprint regions in infrared spectroscopy would be different. So that statement is correct. But let's just eliminate options B, C and D. High resolution mass spec, they've got exactly the same formula, so that one would not work. And they would both be oxidized by potassium dichromate and Tollens reagent, so both of those statements are incorrect as well. Question 34. Which compound is the strongest base? So A is a primary amine. The positive inductive effect means the lone pair on the N is more available to accept a proton. So that's a relatively strong base. Option B, the lone pair on the N gets partially delocalized into the benzene ring, so it's less available to accept a proton. NH3 does act as a base, but the primary amine is a stronger base than ammonia. NH4Cl doesn't have a lone pair available to accept a proton, so that's not a base. So the strongest base there is the primary amine. So A is the correct answer. Question 35. Which statement about enzymes is not correct? So the tertiary structure of an enzyme, i.e. the interaction between the R groups of the amino acids, influences which molecules can bind. That's correct because ultimately how they interact determines the shape. Statement B, the action of an enzyme can be inhibited by a molecular ion that binds to the active site. That's correct. You may have heard or come across of competitive inhibition. So a molecule binds to the active site, preventing the actual substrate from binding. Enzymes work equally well on both optical isomers of a substrate. That's an incorrect statement. So active sites are stereospecific. So only molecules with certain shapes will fit into their active sites. You might have come across examples of thalidomide, where one optical isomer worked effectively as an anti-sickness drug and the other unfortunately led to birth defects. Ibuprofen is another example. So it exists as enantiomers. One of the enantiomers is effective at treating pain. The other one has no effect on the body. So statement C is an incorrect statement. And statement D, computers and as we go forward, artificial intelligence is used to design drugs to block active sites, so they can design molecules of very specific shapes. So D is a correct statement as well. And finally, question 36. Cisplatin has the formula PtNH3Cl2. So it is a square planar complex. So you've got your two chlorines on one side, two chlorides, two NH3s on the other. What happens when it bonds to guanine in DNA? So the chloride platinum bond is quite weak. The chloride breaks off and bonds to the N on one guanine. The second chloride breaks off and bonds to an N on another guanine. That causes the DNA strand to kink, and therefore DNA replication can't occur, so therefore making it an effective anti-cancer drug. So answer D is the correct statement there.